So I think you can probably imagine today is one of those days where I earn my paycheck. The one person in this room that you really don't want to be is me. Because I have the unenviable task of helping you understand chapter 19. So guys, I'd like to talk with you a little bit about how we're going to approach this, because it actually is as intimidating as maybe it might seem. So the topic for today, of course, is entropy and the second law of thermodynamics. Now, guys, if you remember how we handled calorimetry and Hess's law, we broke that into 2 days. We spent a day on calorimetry, we spent a day on Hess's law, and those ended up being 2 very full days. Well, guys, we are going to do something similar here in chapter 19. We are going to spend a day talking about, well, let me say it differently. We are not going to break this into entropy and the second law of thermo. Those 2 are very tightly related. What we are going to do is this. We are going to spend today and we are going to talk about some terminology. And we're going to talk about some underlying principles that you've got to understand in order for this stuff to make sense. And guys, along the way, I'm going to pose sort of an interesting, or at least I find it interesting, question to you. But we're not going to answer it. We are going to leave that question unanswered until Monday, as we then regather on Monday and have this conversation about entropy and the second law of thermo. So guys, what we are going to accomplish today is beginning to get a sense of the underlying concepts that you need in order to do this well. So to do that, what I want to do is I actually want to start with this question. And guys, I don't ask this hypothetically. And if you can't answer this question, then I've failed you. Because if you can't answer this question, then the summary strategy that I chose to have you implement during chapter 19 was ineffective. But guys, remember we did concepts, equations, constants, and diagrams. And somewhere buried down inside your concept section is the answer to this question. And guys, there is an answer to this question. It's not like English class where everybody's answers are good and meaningful and right, which you guys understand is a bunch of BS anyway. I know, right? I just killed the conversation. But guys, I would be willing to bet you that if we chip away at this, we'll be able to figure out what that critical issue is. And I heard you, remember when I sort of did the lean around the monitor thing a second ago and went, chapter 19, guys. And I heard you guys start to talk about some of these difficult concepts that were in chapter 19. So, guys, I'm not looking for the right answer. What I'd like to do is build us towards the right answer collectively. So what are those big nuggets in chapter 19 that you're scared of? Okay, so entropy, right? And guys, what you're going to find out is that entropy is actually an interesting concept on its own. But when we take entropy and marry it together with enthalpy, chapter 5, when we take entropy and marry it together with enthalpy, we get this magical new thermodynamic concept called Gibbs free energy. And Gibbs free energy, you're going to find out, is the answer to this most important question. But that doesn't get us closer to the most important question. So guys, what were the other big nuggets in chapter 19? Reversibility, spontaneity, randomness, what else? Not Gibbs?
No, there was another guy in there. He had a group. There
Oh. Oh, is it Boltzmann? Oh, that's interesting. We're not going to get into Boltzmann until we get into electrochem. So you can forget about Boltzmann.
He had a bunch of equations, and I was like, oh boy.
Yeah. Yeah. No, we're not going to get into Boltzmann.
So ignore that part of chapter.
Okay. So guys, here's what we've got. We've got this idea of entropy. We've got this idea of randomness, which are tightly connected. We just mentioned the idea that entropy or randomness will marry together with enthalpy to help us understand something called Gibbs free energy. It will be Gibbs free energy that will then allow us to answer the most important question, not only in chapter 19, but in this entire unit. And guys, that single most important question, which we're going to start to flesh out today, is what chemical processes are spontaneous? So what we're going to do today is we are going to talk about reversible and irreversible reactions. And as we talk about reversible and irreversible reactions, we're going to talk about how that ties together with spontaneity. Then in the same way that, remember when we played around with the brass block and we talked about energy in, energy out and did all of that stuff? Guys, we're going to have a similar conversation. We did that with kinetic potential energy, internal energy, system surroundings, all of that good stuff. We're going to play a similar game to wrap up today, but rather than move a metal block around, we're going to move an egg around. And we're going to talk about the terms that we share in the same way that we use the metal block to draw together internal energy, kinetic potential, all of that stuff. We're going to use an egg to draw together the idea of reversible and irreversible processes and spontaneity. That's where we're going to stop today. Then what we're going to do when we get together Monday is we're going to bring all of this together and talk about how that relates to the most important question in chapter 19, which is when are reactions spontaneous and when are they not? So guys, let me see if I can sort of lay out the field, if you will, for this day. So guys, this is it. The most important concept in chapter 19, and therefore the most important concept in this unit, is spontaneous processes. Guys, all of this is coming like a symphony towards this crescendo, which is actually spontaneity. Everything that we've been doing with enthalpy and what we'll do with entropy is all building towards spontaneity. So let's talk briefly about what this means. So guys, when we talk about a spontaneous process, what we are talking about is a process that happens without any external intervention. So guys, what does that mean that a process happens without any external intervention? So as we talk about what that means, what we need to do is talk about some of the fundamental characteristic properties of these spontaneous reactions. So let's talk about these, and I think that this will probably help you pull these ideas together. So again, here's what we know. We know that chapter 19 is rough. And we know that there's a lot of really deep, interesting chemistry coming our way. But guys, we also know that this is all headed in one direction. And this one direction is moving towards identifying what we call spontaneous processes. And I think you probably picked up from the reading that you understand that spontaneous processes are processes that happen without any external intervention. So, what are some of the characteristics that make reactions spontaneous? And guys, it's fundamentally this. Spontaneous processes lose energy to their surroundings. Now, guys, it's at this point that we need to be sort of careful. So here's what we're saying. We care about reactions or processes that are spontaneous. What does it mean to be spontaneous? It means happens on its own. So what is it that makes reactions spontaneous? They happen on their own. Well, guys, the answer is spontaneous processes lose energy to their surroundings. So, guys, you ready? Tie this back to chapter 5. Does that mean that they're endo or exothermic? They are exothermic. But guys, the thing that makes this interesting is many times we don't think of these as being heat-releasing processes. But guys, let's tie this back to our, ouch, hurting me. Okay, let's tie this back to our metal block. Okay, so the idea is this, and I'm going to use this as a bumper. I'll use my book. Okay, so guys, the thought here then is this. If I've got this metal block suspended here in space, and if I let go of the block, what's going to happen? Are you sure? Is it really going to fall? Okay, but hold on. In order to get it to fall, do I have to stand up here, and when I let go, do I have to push on it to make it fall? Or will this fall all on its own? It's going to fall all on its own every single time. So why does it fall every single time? Not, well, gravity, but relative to energy, what do we know has got to be happening? It's losing energy. And do you remember when we did the metal block thing? And we said that as this falls, where does the energy go? Well, so the energy is being lost is friction to the air. But what is happening to the total internal energy to this block as it falls? Stays the same, good. So potential is becoming kinetic. And then when does it finally release all that energy? When it hits here and it's released in the form of work and heat, because it heats up the book and it does work as it pushes the air. But guys, what we know for sure is first of all this. Do blocks always fall when they're released? So what does that make it? Spontaneous. And if it's spontaneous, we know that it's losing energy, because if it's losing energy, it's got to be spontaneous. Do you buy it? Okay, go ahead. Well, and that's what makes it fall, right? We're not talking about forces, we're talking about the process itself. Gravity is the force that causes that to happen. Oh, I see what you're saying. So, I get, okay. But understand that when we understand that we're talking about energy, right? And what did we find out that all energy is dependent upon when it comes to storage? Attraction. There's always got to be attraction, right? So when we say, where did it go? No outside intervention. Realize that we can't isolate our universe from forces of attraction. They're the very fabric of what makes up the universe. So when we say no outside intervention, we're not talking about the underlying forces that cause energy exchange to be possible in the first place. Let me give you another example. Okay, you understand about, let me do this differently. So here we've got, now we'll do it like this. Here we've got a hill, and I know this was in the book, but now we've got a ball at the top of the hill. And guys, if that ball is anywhere over, so let's say it's not there, let's say that that ball is actually resting right here, and it's a little bit past the crest. Will that ball stay there? What's it gonna do? Roll downhill every time? Yeah. Will it ever roll uphill? Will it ever go from here and get right up here on the top and go, oh, look, I got to the top? No, it will always roll downhill. Now, you're right, it takes gravity, right? So when we say no outside intervention, we are not excluding things like gravity and attractive forces that cause this to happen, but we are saying there's no outside player that causes this ball to roll downhill. Are you comfortable with the idea? Yeah. Hold on, to go over this way?
Yes.
Okay, keep going.
That wouldn't be spontaneous because you would have had to add energy to get it up to the point where it would become.
Correct. So that is something that takes outside intervention. And Mark, you're touching on something that's going to be very confusing as we move down the road. So let's do this. And guys, catch this idea. Do balls always roll downhill? Yeah, that's spontaneous. Can balls move uphill? Yes, but not on their own. And we call that non-spontaneous. So what you're going to find out is that every process in this universe, whether it's balls rolling downhill or stars turning hydrogen into helium or chemical reactions, it doesn't matter. Every process in this universe has a reaction that we call the spontaneous direction. It's what happens all on its own. But all of those processes also can go in the other direction. It's called the non-spontaneous direction. And are non-spontaneous processes possible? Absolutely. But for a non-spontaneous process to take place, what has to be there? Outside intervention. Does that make sense? So can a ball roll uphill? Oh, baby. But it doesn't do it on its own. Somebody's got to push the ball to the top of the hill. Does that make sense? You doing okay? Okay, so now guys, what about this? Burning hydrocarbons. Does this happen all on its own? Now it's getting a little more muddied, right? So guys, if I just do this, and if I just push down the lever, the gas is still coming out of here, but it's not combusting. But when I do this, and I add a little bit of energy in the form of a spark, now it starts to combust. So now let's talk about it. Is the burning of a hydrocarbon, in this case butane, is the burning of butane spontaneous? And guys, it's a little bit harder question to answer, right? Why is this harder to determine if it's spontaneous? What made it muddied? Exactly. It's the difference between burning and igniting, right? And guys, here's the other thing you've got to understand about spontaneity. The initial ignition does not violate the idea of outside intervention. So the thought then becomes this: once this starts to burn, do we need to do anything to make it continue to burn? It burns on its own, right? That is still spontaneous. So understand that an initial input of energy that is required to get something started. And do you guys remember the name of that input of energy that you learned last year? Activation energy. Do you remember that? Yeah. So guys, this amount of energy, which is called activation energy, does not refute the idea that this is still a spontaneous process. So we disregard activation energies when we think about spontaneity. Is that okay? So now the questions again. Go ahead.
So then how is shoving that ball, giving that ball a little shove, how is that not?
Okay, so but it's the difference between that and this. Understand that rather than think about the ball, think about the block. Okay, can this block fall on its own? No, I've got to hold it up here and hang on to it, right? So there's some energy that's being engaged with this block just by me holding it there, but it's at that moment that it starts to fall that it happens spontaneously. Relative to the ball, think about it this way. So imagine, did you guys understand Jake's question? Yeah. What about the ball? Okay, so let's do it. So the difference is this. Imagine that instead of the ball being right on the, can I say precipice? What if the ball's here? Okay, if I start to push the ball uphill, will it move uphill? What if I stop pushing? It doesn't keep going uphill. Do you see the difference? So yeah, we can add energy to this to get the ball rolling, no pun. But the idea is if I stop pushing, that thing's going to stop doing what I'm pushing it to do. Unlike my lighter, because all I have to do is an initial input of energy, but I don't have to keep doing that. I don't have to keep pushing to keep this going. Do you see what I'm saying? And so that initial input of energy does not make it non-spontaneous. That was a really weird sentence. But if it requires that we keep pushing, then it's not spontaneous. Go ahead. That's equilibrium. But okay, but let's do it. If it's at the very top of the hill, which direction does it want to go? Either one. And that is closer to the condition of equilibrium. What you're going to find out, and I'll give this to you now because the moment's right, when a system is at equilibrium, it's actually spontaneous in both directions. Yeah? They did. It's not they did. Yeah. So go ahead.
So if you were to throw that ball.
No. Go ahead, Matt.
So to the question, there could be more than two directions, though, right? Like the ball rolls to the other side.
No, I understand what you're saying. So guys, Matt's question is, can there be more than two directions, forward and backward? And now we need to bring this to the world of chemistry. And this is something that we haven't talked about, but we'll do this really quickly. Chemical reactions start at reactants and end up at products, okay? So your question was, can there be more than one direction? Because it would seem like in chemistry, we've got two directions. Reactants becoming products, products turning back into reactants, okay? It turns out that for now, we're going to say no. There's only two ways to go, forward and backward. The thing that we're going to bring into this conversation in 2 units is that there are actually different ways that you can go forward and different ways that you can go backwards. Those are called reaction pathways, and they have a lot to do with spontaneity, and that's actually how catalysts work. Catalysts actually drop the amount of energy that's necessary for the reaction to be spontaneous by providing a different pathway. So the big answer is yes, there can be more than one forward and reverse. You're still going from reactants to products, but how you get there can be different. But for now, relative to what we're doing in this unit, we're just going to say one way forward, one way back. Is that okay? Okay, so guys, here's where we are right now. We understand this idea that reactions can be processes, can be spontaneous. We understand that spontaneous happens on its own without outside intervention. Brandon brought in the idea that, wait a minute, what about gravity? Gravity is really an outside force, but we're understanding that we've got to discount that idea because we can't escape these outside forces. And then Jake got us thinking better about this idea of the initial push. And we understand now that there's a difference between this ball teetering up here and needing a little touch to start moving, and this idea that we could, yes, push the ball uphill. The difference being, after that initial input of energy, if when we stop inputting energy, the process stops, it's not spontaneous. Like the ball being pushed uphill, we stop pushing, it goes back down. Unlike the lighter, where we add a little bit of energy and it burns, and we don't have to keep flicking this thing to keep it burning. Do you see the distinctions? Okay. So, guys, we've now included these two ideas, balls rolling downhill and hydrocarbons burning. But now, guys, we need to bring up another interesting thought about this idea of spontaneity. Yes or no? Nails rusting. Is that spontaneous? So what does it take to get a nail to rust? Literally not. Well, it takes oxygen. It's accelerated by water or metals or acids. But guys, if you've ever found a nail that you're building a project, you left it out in the yard, it sat there over the winter, you come out, that sucker's rusted. Did you have to do anything to coax that nail into rusting? Okay, but relative, guys, to butane burning, and you guys understand that these are the same chemical processes. What is this butane reacting with? Oxygen. In order for nails to rust, what does it have to react with? You said that earlier, right? Guys, these are both oxidative processes. They are both spontaneous, but guys, nails rusting is way slower, okay? Here's the thing they're going to trick you with on the AP test. Rate has nothing to do with spontaneity. Something can be wildly spontaneous and really stinking slow. So guys, don't confuse spontaneous with fast. And I don't know what you need to write down to remember that. But guys, do not confuse spontaneous with fast. Something can be highly spontaneous and it can move at a snail's pace. So spontaneous does not mean fast. Spontaneous means happens by itself. You okay? Okay. Go ahead.
If you took like a beaker of water, the other room temperature, and you put it in a warmer room,
Okay.
it warmed up. And you're saying that would be spontaneous, but then if you put it on the Bunsen burner and have it back, and heat up,
Sure.
that would be spontaneous.
No, it would still be spontaneous because you still have an outside source of energy that is being moved in. So whether it's the room or whether it's a Bunsen burner, the question is, the bigger question is this. When you put something cold in an environment that is warmer, do you have to do anything to get that heat to transfer from hot to cold? So it's spontaneous. It doesn't matter if that hotter environment is a warm room or the presence of a Bunsen burner. The bigger question is, does heat move from hot to cold spontaneously? And the answer is absolutely. Yeah, go ahead. Did I really say highly spontaneous? No, bad, no, bad, no, no, no. No, guys, no. No, there's no such thing as highly spontaneous. It's like an on-off switch. Either it is or it isn't. No, either something is thank you. Either something is spontaneous or it's not. There are not degrees of spontaneity. There are degrees of rate. I'm really glad you caught that. But there are not degrees of spontaneity. Either it is or it ain't. You okay? Okay. So now, guys, let's come back to our central principle. What do all three of these spontaneous processes have in common? They lose energy. Do you get it? So, spontaneous means happens on its own, and we understand that spontaneous processes lose energy. So now, guys, let's think about why that would be true. So, guys, how do we get energy between system and surroundings? Work and heat, right? And so, guys, if we have a system and if we want something spontaneous to happen to that system, what does that system have to do with energy? Get rid of it. Does that make sense? Okay, think about this, guys. This is important. So we've got a system, whether it's butane burning or a ball rolling downhill or a nail rusting. That's our system. And if something's going to happen to that system that's spontaneous, it's going to get rid of heat. And that's easy because you're always surrounded by surroundings and you can just get rid of heat. But in order for the other process to take place, then the surroundings would have to give energy to the system. Does that make sense? And that's not always guaranteed. Your surroundings may not be able to or may not want to give you energy. Go back to our block. Will that block ever rise? Why not? Because I'm choosing not to give it energy. See, when this block falls, it's going to give away energy and there's nothing I can do about it. That's spontaneous. But guys, could that block rise? But what has to happen? I've got to do work. I've got to give that energy, and the block has no control over whether or not I'm going to give it energy, and if I choose not to, it's not going anywhere. So guys, you can think about it that way, that spontaneous processes are processes that the block has control over. This block is always going to fall, is always going to fall because it's easy for it to give away energy. It just does it. But if it requires the surroundings to help out the block to make it go up, the surroundings may not want or be able to do that, and it ain't going to happen, making it not spontaneous. Does that make sense? Okay. Now, guys, you're not going to like this. Here's what we know. Spontaneous processes happen on their own. Here's what we know. Spontaneous processes lose energy. Here's what you know. Spontaneous processes by definition lose energy because the system can always lose energy to the surroundings. The other is not necessarily true. You get it? Now watch this. And guys, I know this is going to kill you because I know you. You know what these are? It's a quick cold pack. And if you don't know how a quick cold pack works, you can hear the pellets, right? These are actually pellets of a salt, ammonium nitrate, NH4NO3, ammonium nitrate. It's actually one of the major components of lawn fertilizer. This is pure though. These are pellets of ammonium nitrate. If you put this on your lawn, it would kill it. It's too concentrated. But guys, this is ammonium nitrate, and then inside here, there is a bladder. And inside that bladder is water. Now, does ammonium nitrate dissolve in water? Oh, baby. All nitrates are soluble in water, and all ammonium compounds are soluble in water. This is like double sure it's going to dissolve. But guys, here's the trick. How do you make this work? And I'm not going to do it. But what you do is you squish it. And when you squish it, the bladder of water inside ruptures. The water leaks out into the ammonium nitrate, and the ammonium nitrate dissolves into the water. So what is the chemical process that's going on inside here? Ammonium nitrate dissolving in water. Is that endo or exothermic? Endothermic. How do you know? Because this is a cold pack. Okay? So when this ruptures and that process happens, you then hold this against your injured body part, and it sucks heat out of your injured body part, which you experience as cold. Heat is transferring from your hot body part into this endothermic process, and it's sucking out heat. So guys, this is an endothermic process. Now here's the trick. Is it spontaneous? So, when I break this bladder, all I'm doing is mixing the water and the ammonium nitrate together. Now, do I have to keep shaking it to make sure it stays cold? No. Once, in the same way, guys, that I light the lighter and then it goes all by itself, all I got to do is go pop, and this thing goes on its own. So, ammonium nitrate dissolving in water. Is it spontaneous? How do you know? Because it happens without me forcing it to. Yes? Don't confuse allowing it to. Just a second. Don't confuse allowing it to with forcing it to. All I've got to do is bring them together and they go from there. So guys, focus here. Is it spontaneous? Yes. No, it is. Guys, and if you don't it is. And if you don't understand why, let's talk. Hold on, Rebecca. I break the bladder, the ammonium nitrate and the water mixed together, okay? And that process, that ammonium nitrate just dissolves in the water, and it keeps dissolving, and it keeps dissolving, and it keeps dissolving until all the ammonium nitrate is gone. Okay? I don't have to stir it. I don't have to shake it. I don't have to move it to get it to dissolve. It is spontaneous. That's not open for debate. It is spontaneous. Now, is it endo or exothermic? It's endothermic. How do we know? Because it's getting cold. Do you see the problem? We now have an endothermic process that, where did it go? That does not lose energy. Guys, we now have a spontaneous process that doesn't lose energy. And that violates everything that we just talked about related to spontaneity. Because we understand that balls roll downhill. Why? They're giving off energy. We understand butane burns. Why? It's giving off energy. We understand that nails rust. Why? They're giving off energy. Well, guys, guess what? Ammonium nitrate dissolves in water. Why? It's not giving off heat energy. So, guys, what's going on? Guess what? I'm not going to tell you. But guys, I will tell you this, and I'm ignoring you. Guys, I will tell you this, and you can write it down if you like. Guys, quick cold packs are an exception to this rule. So if you don't understand why this is an exception, I've written it out for you in sentence form. The idea is this. Energy must be lost to the surroundings in order for a reaction to be spontaneous. That is true. But if that is true, what explains what we're experiencing with a quick cold pack? And guys, the answer is simply this. Our definition of energy is too narrow. But we are not going to expand our understanding of energy until Monday. I know. Well, but we're not quite done. There's 2 more terms that we need to talk about. Okay. So guys, let's summarize here to make sure you're clear. Spontaneous means go, and understand we're not close to done, but this is a good connecting point. So guys, here's what we know. We know that spontaneous means happens on its own. We understand that in order for a process to be spontaneous, it's got to lose energy. Balls roll downhill, they lose energy. Nails rust, they lose energy. Hydrocarbons like butane and a lighter burn, they lose energy. We established a universal principle that says anything that happens spontaneously must lose energy. But then we brought in the quick cold pack, and we came into what was seemingly a contradiction. Because is this spontaneous? Yes. Does it lose energy? And on the surface, it would appear as if it doesn't because it's endothermic, meaning it's taking in energy. So now we've got a seeming contradiction. It is spontaneous, but it is not giving off energy. And that's where the tension lies for us. But what we're going to find out is that, in fact, the tension doesn't exist. This is giving off energy, but it's not in the form of heat. And I'll tell you the answer. It's in the form of disorder.
Yes. I told myself, I said entropy.
But we're going to talk more about what that means on Monday. But guys, understand, to really grasp well Monday, there's 2 more terms we need to talk about, and it's how we're going to finish today. Go ahead, Valerie. Why? Why does that seem? My response seems flippant, but I really, you're onto something important. Why does that seem weird to you? What if I told you this? What if I told you it does? When nails rust, it actually gives off quite a bit of energy. If you can concentrate that reaction, have you guys ever used hot packs? You know, the things that you break them and shake them? The reaction that takes place inside of those hot packs is actually rusting iron. Yeah, so it does. So why is it that you understand that hot packs, which you now know to be rusting iron, is exothermic, but you don't think of that with nails? Because it happens so slow. So the energy is being released, but it's being released over such a large amount of time that you're unaware of it. So why do the hot packs go faster? More surface area. They grind up the iron. And then they add substances that make it go faster. Okay. You guys with me? All right. So guys, this is the way we're going to wrap up today. Little bit of terminology. And these are some terms that you were talking about at the beginning of the day. Guys, term number 1 is a reversible process. Guys, in order for these next couple terms to make sense to you, you have got to weed out of your brain right now the idea of spontaneous. So don't try to connect these terms to spontaneous until I take you there. Reversible process. Guys, a reversible process is a process that can return to its original conditions, its original state, with no change in the system or the surroundings. So guys, just let that, don't think about it too much, just let it sit on its own. So a reversible process is a process that can go from where it went back to where it started with no net change in the system and the surroundings. Now guys, if you allow that to stand on its own, and if you spend some time and chew on it, you're like, what on stinking earth does that mean? And guys, the reason that you're having a hard time chewing on it is because in your daily experience, you don't run into a whole lot of stuff that are reversible processes. It's not because they don't occur, it's because we're unaware of their occurrence. Why would we be unaware of their occurrence? Nothing's changing. They're moving forward and backward at the same time, and we don't observe anything changing because they're moving forward and backward. But now all of a sudden it sounds familiar, right? What do we call processes that go forward and backward at the same time? Equilibrium, right? You may want to write it down. These are systems that are at equilibrium. But Matt's exactly right. The reason it's hard for us to connect with that concept is we don't see any net change because it's at equilibrium. So guys, allow me to just hijack from the book the example that they use, because it's helpful for me to think about at least what could be a practical example. So guys, the book gives you this example. A glass of ice water at 0 degrees Celsius. Here's the thing, chances are good you've never seen this. So guys, you may want to draw it with me. So here's the idea. You've got a glass, and let's just put one ice cube in the middle. So you've got a glass of ice water. So you ready? What if you were to take this glass of ice water and set it right here on the table? What's going to happen? The ice is going to melt. What happens if you take this glass of ice water and you put it in the freezer? It's going to freeze. But guys, what would happen if you took this cup of ice water and you put it in an environment where the temperature was exactly 0 Celsius? And do you understand that in your freezer the temperatures are sub-zero? So what would happen if you put this glass of ice water in an environment that was exactly 0 Celsius? Would it melt or would it freeze? Yes. It would do both. Guys, and check this out. Here's the idea. Imagine that this is a water molecule. So does that water molecule have more or less energy than the molecules in the ice cube? Let's do this. I'll even try to switch colors here. We'll go red. Okay, so the black ball is a liquid water molecule. The red ball is an ice molecule. Which one has more energy? The liquid one, because it's broken the lattice apart and is escaped from the lattice of the ice. Now guys, here's what happens. These water molecules are moving around, right? So when this water molecule crashes into the surface of the ice, what does it do? Loses energy to the ice. And as it loses energy to the ice, it freezes and sticks to the surface of the ice. But where does that energy go? into a molecule on the surface of the ice, and that molecule gains the energy, comes off and melts. So for every molecule that freezes, a molecule melts, and consequently there's no net change. Remember, no net change in the system and the surroundings, which by definition is a reversible process. I fear to go there because there's a lot of other forces at play there. You know that eventually that'll stop, right? So I'd hate to go there. So guys, these are then at equilibrium. Does that make sense? Okay. No, not at 0 Celsius. Good on you. Guys, did you hear Uriah's point? He said, wouldn't that stop too? And the answer is no. At 0 Celsius, not only would it never stop, but as Matt said, we would never notice a change. Because the number of molecules tied up in the ice and the number of molecules in the liquid water would never change because they're always exchanging perfectly. Does that make sense? Okay. All right, guys, so now let's look. Go ahead. Well, that's a whole nother class of chemistry because you're actually talking about the way crystals form. And the answer would probably be no, because you've probably seen that sometimes when you make ice, it's very clear and translucent, and sometimes when you make ice, it's cloudy. The reason is because the order with which the molecules froze when the ice formed. So it might look a little different because of the efficiency of the crystal formation. So technically, it may not look exactly the same. So, okay. So guys, now let's talk about irreversible processes. Unlike reversible processes, irreversible processes cannot simply be undone by reversing the events that caused it. Now, guys, don't be confused. If irreversible processes can't be undone by simply doing the opposite of what did them, like melting and freezing, right? When one melts, the other freezes. When one freezes, the other melts. They're just undoing each other. Guys, in a reversible process, it's not like melting and freezing. It's one process cannot be undone by doing the reverse process. But that does not mean it can't go backwards. It can go backwards. It just has to go backwards through a different path. And guys, that different path has different amounts of heat and work associated with it. Okay. You caught up? You're good? Okay, so what does all this mean? Let's go here, and let's go here, and let's go here. And guys, let's look at reversible and irreversible processes. So guys, here we have an egg, and I'm going to show this to you through this little animation, and then we're going to talk about it more, allowing this piece of paper to represent the egg. Okay. So guys, we've got some eggs, and these eggs are suspended in the air. We've got some eggs, and these eggs are suspended in the air. When we let go of these eggs, what are they going to do? They are going to fall. Do we need to do anything to convince them to fall? They will fall all on their own, and splat, they're done. We understand that that is a spontaneous process. But now let's tie the concept to reversibility. Is this a reversible or an irreversible process? Okay, hold on. You're saying irreversible, and what does irreversible mean? Can't go back through the same pathway. Now guys, check this out. Can this process be reversed? Yeah. It is actually technically possible to gather up the eggshells, tuck the yolk, tuck the white, tuck everything back inside, and perfectly at the atomic level, knit all of that back together, turn these into totally pristine eggs, and then lift them back up to the hand. But is that going to be as easy as just dropping them and watching them go splat? No, and don't miss this, guys. You know what that's going to take? A lot of work. To make it go the other way, it's going to take a lot of work. But guys, you ready for a really crazy thought? Check this out. That never happens, right? Now, guys, watch. These are going to fall all on their own, right? Spontaneous. Why is that spontaneous? Why is it? I know that's, but why is it spontaneous? Gives off energy. Yeah? Now, in order to get the eggs to come back together and go up to the hand, what's going to happen? We're going to have to add energy. You ready for a crazy thought? How much energy has to go in to put the eggs back together and pick them up compared to the amount of energy that was given off when they fell? It's exactly the same amount. The difference is this. Getting these to go back up is going to take a lot more work. When the eggs fell, there was less work involved and more of the energy was lost as heat. To get those eggs back together and raise them back up to the hand, it's going to require more work and less heat to get the eggs back up where they began, indicating that it doesn't go through the same pathway. But it can be done. So guys, this is the important thought then. Eggs falling, is it spontaneous? Yes. Is it reversible or irreversible? It is irreversible. But wait a minute, we just said that we could undo it. So then not through the same pathway. Guys, let's say that again because that's critical to what we're going to talk about Monday. Eggs dropping and splatting. Eggs dropping and splatting. Spontaneous, yes or no? Yes. Is it reversible or irreversible? Irreversible. How do we know? Can it be undone? Yes, but it requires different work and heat inputs to make it go backwards. But again, the crazy thought is the total amount of energy that would take to get it back is the same as the amount of energy released. Yes, it would still be irreversible because that ball will not just magically rise. But, and you saw this with the block, the amount of energy that it took me to raise it up is equivalent to the amount of energy that dropped when it fell, right? The thing that simplifies that model is that when the ball falls, it doesn't splatter. But the energy math is equivalent. Is that okay? Okay, so guys, coming back then to our big idea, the idea is this. We understand reversible and irreversible. What does it have to do with spontaneity? Here it is, guys. And you don't need to write this first one down. You already know this. Spontaneous processes are processes that happen without any outside assistance. This is then the connection. Spontaneous processes always happen in what we call the spontaneous direction. Why do we talk about a spontaneous direction? Because they're irreversible. Spontaneous processes are irreversible. So spontaneous processes have a direction that we call the spontaneous direction. They have a direction we call the non-spontaneous direction. The spontaneous direction is the one that we see happen because it's the one that releases energy. And we'll explain how that's still the case with the quick cold pack next time. Yeah. equilibrium can be thought of as being spontaneous in both directions simultaneously. It's exactly, it's going both directions at once. Yeah. Okay. So guys, really quickly, let's go over pride reports. Tyler, you are going to stay. Oh wait, hold on. Sorry. I shouldn't record this.